Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be launching into the first of our three laws of thermodynamics. And that'll be the first law, which is don't talk about thermodynamics. So we left off talking about internal energy. And it turns out trying to measure the total internal energy of a system is actually quite hard. And it's not so much because of the kinetic energy term, it's that potential energy term because it turns out there's a lot of different ways you can store energy. I definitely say too many. So some examples are that you can literally store it as gravitational potential. So that's literally in the position, how high you are off the ground. You can put things in magnetic fields and you can have a magnetic potential energy. The one we're often more interested in is chemical potential energy. So that's going to be the stuff, the energy stored in chemical bonds. But you also have nuclear potential energy, which is the amount of energy stuck in the actual atomic configurations. It turns out that most of the time we don't care about most of these because a lot of the times, very few of these are going to actually change. I'm really not throwing my flask around, so I could probably ignore gravitational. Most of the time, I can often ignore magnetic. Some cases you can on each of these. I'm not doing nuclear chemistry, so I can probably ignore nuclear potential. So we're often going to focus more on kinetic and chemical. So again, our thermo energy and our energy stuck in bonds. Though oftentimes we're going to start really by looking at the kinetic and not playing around too much with the chemical potential right away. We'll work our way up to it though. And so if most of these aren't going to change, why bother change during a reaction? Why bother calculating the total potential energy or internal energy? Instead, we're often going to focus on how the internal energy changes. So again, representing change by this delta U. So if the energy increases, we see we'd see the delta U be positive, decreases negative. Now here's where we can make use of something very useful, which is the fact that um, the internal change in internal energy for an isolated system should be zero. So if I look at the universe as my system, well, I can't be bringing energy into the system, nor can I be putting energy out of the system because the universe is by definition everything. And so the major idea with this first law is that I can't create or destroy energy. This is just another way of talking about this first law of thermodynamics. So this relationship is going to hold for any isolated system. And this is really what we call with our first law of thermodynamics. And colloquially, this is known as the idea of conservation of energy, or the fact that energy can't be created or destroyed, only moved around. So we can move energy from thermal into chemical potential or vice versa, but I can't go ahead and just spontaneously change the energy of an isolated system. Turns out it means there's no such thing as free energy. I can't spontaneously create energy and then use it for reaction. The energy always has to come from somewhere. And the idea of creating energy from nowhere is kind of the idea of perpetual motion. And it turns out that this is such an important phenomenon that after a lot of antics in the late 1800s, early 1900s, where every crackpot inventor would come up with their own perpetual motion device. So around 1911, the patent office said it refuse it refuses to let anyone file a patent for a perpetual motion machine, though this hasn't stopped people from trying. One of the most notable cases was in 1979, where Joseph Newman, as you can see here on the right, he had come up with a machine that was a net producer of energy. It was an eternal source of energy. And he filed his patent, and the US Patent Office says, well, this smacks of perpetual motion, you're denied. He appealed to the courts, and the courts signed a special auditor named William Schuler, who was the former patent office commissioner. And he assessed the device and said, hey, it works. It meets its claims. The judge says, well, I still don't think it, so I'm going to put it to a special committee to the to the Bureau of Standards, who found that it didn't work. And so because of the commissioner's recommendation, he brought this all the way up to a special Senate committee, where famous astronaut John Glenn pointed out that it wasn't possible. Didn't get a lot of buyers on the Senate committee. And then he pointed out that Schuler's, so the commissioner, his law firm actually filed the original patent. And while the Senate might not recognize the laws of thermodynamics, they can see a conflict of interest when it rears its ugly head. And so it also shows that there's just some laws you can't change or overturn as much as Joseph Newman wanted to. You can't create energy from nowhere. It's just not possible. So, if we're going to look at how internal energy changes, this means we have to look at how it enters and exits the system. So, we can imagine energy entering and exiting the system in two key ways. The first is heat, which, my apologies, is represented as Q. And this is going to be the transfer of kinetic thermal energy. So that random kinetic energy from an area of high concentration to an area of low concentration, which is another way of just saying energy goes from high temperature to low temperature. So whichever side is lower temperature, the heat energy or that thermal motion, that kinetic energy will move from the hot source to the cold source, whichever direction that is. So this is one you might be a little more familiar with. The other one you mostly saw in physics is this work that we brought up last time. So work is going to be the usable energy. So the amount of energy I can use to make this system move against an opposing force. So either I can go ahead and put work into the system or pull it out of the system. Now, the idea, if we're mostly assuming that energy can enter or exit the system either as heat or work, this means I can express the change in internal energy as just the sum of these two. So at this point, we need to start paying attention to signs, which is a very tricky subject in this class. So the major idea is if energy is entering into the system as heat, as work, or as just the increase in energy, all of these are going to be positive. That means that the energy in the system is increasing. Do watch out. There is a different sign notation for work in physics, but for chemistry, any energy entering the system has a positive sign. Conversely, if energy leaves the system, so if energy leaves the system as heat or work, that is a negative sign, or if there is a decrease in energy in the system, that is a negative sign on the internal energy. Now, one of the things I want you to pay attention to here is notice that when expressing the change in internal energy as heat and work, internal energy has a delta sign indicating a changing property. Heat and work don't. Now, the reason why heat and work don't have this delta sign is they're what are referred to as path functions. And this is the idea that heat and work are talking about how things are moving. They don't refer to to a given initial or final state. So for example, if I tell you how much heat I apply to a system, I still don't know anything about the final state because it doesn't tell me about the energy in the system. If I have a known amount of heat, in order to actually figure out what the final state is, which again is going to be that internal energy, it turns out I also need to know about the work. So for example, if I pull heat from the system, I have a decrease in energy, internal energy. But is that all from heat? Or did work provide some of that energy? Or is there actually or as I lost heat from the system, did I put some work into the system, which cancels out a bit of this? So it turns out it isn't sufficient to know only the heat or only the work. In order to tell anything about the state of the system, I need to know both. So again, another way you can identify it is if you have a state function. This means you have an initial state and a final state. So we'll see changes represented with deltas. If there is a change and there is no delta, that's a good indication we're looking at a path function. But a useful thing about path functions is that while a path function alone might not give you any information about the state, two path functions can often produce a state function. So as a result, often when we're looking at systems, we're going to constrain the system so I know something about heat or I know something about work. That way, I'll have an easier time determining the internal energy of the system. Now, we can go ahead and represent this change in internal energy on a discrete basis, but it's often much more common and much more useful to go to calculus and represent everything on an infinitesimal basis. So looking at how heat work and internal energy changes slowly over time. Again, note an integration over the internal energy will give me a change, whereas an integration over this infinitesimal heat and work just gets me heat and work. So this just brings us to the idea of how can I look at this heat and work of the system. So heat's going to be a little bit more complicated. So we're going to start by looking at this work. So how can we describe the work on the system? So one of the easiest ways we can do this is by looking at either the compression or the expansion of a system. Because if I push down onto the system, I am accomplishing a movement and I will have an opposing force because the gas wants to have a certain volume. It is exerting a pressure against that work. So compression is going to be a very good place to start with this description. Now, this idea of just pushing on a container or a piston of gas may seem to be a fairly simple idea. But it turns out it's actually fairly useful because this idea of moving pistons is going to show up in all kinds of things, um, uh, realistic applications. And the simplest version I can do this is making sure that the force is just simply putting a weight on the piston. So next time we're going to pick up looking at the compression of an ideal gas and how this will change the work and internal energy of the system. Until then, take care.